All right, let's talk composite airframes. So, what do we need to know? Well, we need to know the pluses and the minuses, right? The advantages and the disadvantages of building in composite. And again, there's lots and lots of advantages where literally it's a money thing when it comes to the disadvantages. And so everybody's using composite as their base material for the new design aircraft because of the incredible strength and weight savings. And so weight savings equals money in the bank because it's reduced fuel burn, right? And so from military to commercial to everybody, everybody's using it. So composite is made up of two things, right? It's fabric, and it's also the material that we hold that fabric or support that fabric with, which we call the matrix, right? And so let's start with fabrics. And so what you need to know is the advantages and the disadvantages of each of the different types of materials, starting with as simple as micarta, which is a cotton-based epoxy, to the latest and greatest materials. What are the major pluses and minuses to each of them, and why would we choose to use those particular materials in a particular build? What advantage do they bring to the table that make them a good building material, right? And so we've got our base material, like glass, being in two formats. What is the pluses and minuses of each of those different types of glasses? Kevlar, we know impact resistance being the major plus, and its ability to be fractured or open up if it's damaged and absorb moisture. So that's its major disadvantage, right? And then we talk, carbon fiber. Why are we using carbon fiber? Well, it principally comes down to one format or one strength that makes it a good material to build and to work with. And that principal strength is its ability to take compressive loads. Its rigidity or its stiffness allows not only compressive loads, but it's pretty darn good in torsional or twisting loads. But I mean, and again, like most of the other fabrics, it's really good under tension. But tension's an easy load. But if you want to build something that has strength in all kinds of different types of loads, carbon fiber has some major advantages in its stiffness. Of course, we know, I always think of corrosion resistance as another one of its superpowers, but the problem with it is, of course, when it comes in contact with anything else. It's very high on that galvanic chart, very noble, and so it's going to stay, but it's going to eat the other materials, right? So it can come in all kinds of different designs and formats, from single long strand fiber to some sort of woven fabric, even in chopped format where we're using in things like brakes and other components like that. So again, a very versatile product that has a lot of really good value to it. Boron being the other extreme of the formats there, and so boron's superpower is also its weakness. It's unbelievably stiff, but it's so unbelievably stiff that it's almost impossible to work with. So it's a win-lose situation with the material itself. So there's definitely other fibers out there. Ceramic fiber being good in super high temperature applications, and then materials are changing, and so we get stuff like Spectra and new design materials. As the future rolls out, we're going to see more and more cool fabrics come out that can be used within the composite world. Now, one of our major advantages to composite is its ability to flex within a specific range. So once flex gets to be too much, such as damage, what's going to start to happen is, rather than probably so much dramatic or catastrophic failure, we're going to have potential for delamination, right? We're going to flex those fibers to the point where they can't stay connected anymore, and they're going to start to separate. And as soon as you have materials that aren't fully bonded together, we've lost the strength, right? And so we've got to make sure that we keep that material undamaged undelaminated. And so how are we going to know? Well, the biggest thing again is going to be our visual. Can we see the damage? And in a lot of cases it's going to be super hard, because with that flexibility it will flex, return to its shape, but have a sustained damage, right? And so detailed inspection is the big thing. So around access points on the aircraft where people will be working, where equipment will be working, and having a really good look at those components on the airframe. If we think we have even the remotest chance of there being damage, first quick and easy way of being able to tell, hopefully, will be our tap test, right? Either with a coin or a tap hammer. And so we're going to use those techniques that change in sound. So from materials that are solid, that ring with a high-pitched ring, because the whole unit resonates as a solid mass, as opposed to the dull thuddy noise if you get a material that's been separated. And when it separates, all those separated layers help to stop that ringing. They kind of deaden each other out, and so you get that dull thud. If we think there's the potential that there may be delamination via doing some sort of a tap test, then we're going to get NDT involved to verify unless damage is supervisual, and then we're going to have to carry out some sort of repair. And so if it's a component that is a strong load-bearing type material, then we're going to be looking for something like a step repair. So we would grind out the delaminated layers, and then we would create areas, circles or ovals or whatever the shape may be, of stepped layers. And that way when we put our repairs in to fit in those layers, we're allowing transfer of energy across the repair area, right? And so bringing back strength into that joint. If it's a non-loaded component, we don't necessarily have to worry so much about bringing back strength. And so we would move to something like a scarf repair, where it's literally, take the material out down to the delaminated layers, and then we're just putting patches in as fillers. And so it's more an edge-to-edge contact, which doesn't give us the same degree of strength, right? But still may be strong enough for what we need to do. One of the tools that we'll probably use during that process would be a hot bonder. And so the hot bonder is going to provide us with a couple of things. It's going to provide us with vacuum, it's going to provide us with controlled heat, and it's going to give us some sort of feedback as to exactly what's going on during the repair, right? And so we'll have thermocouples in there on top of our heating blanket, providing the control box with feedback as to the temperature over the repair. That feedback will then control the box to cycle power on and off to our heating pad in order to maintain a very tight temperature range, right? All the time we'll have vacuum provided and some sort of feedback from that vacuum to make sure that we're maintaining vacuum within the area of the repair, right? So a very useful tool. Our heating pads are going to be overlapped because we can't rely on the consistency of heating wires within the outer perimeter of that heating blanket. So we'll overlap them so that we don't end up with a spot where potentially there could be a cold area over the repair. We've got to maintain that even temperature and even pressure over the entire repair. We know that there's warp fibers. So warp fibers, there's always going to be warp fibers, right? So there has to be long-running fibers coming on our fabric. And again, within the aviation field, we're principally going to be putting down materials, probably unidirectional fabrics that only have warp fibers. But depending on the design and the requirements, we may have fibers that have different types of weaves or designs. And so we may have cross 90-degree fibers, which we call our weft or fill fibers. We may have fibers on an angle, in which case we're going to be looking at bias fibers. And so the fiber direction is super critical to providing us with strength in the direction that the fiber runs, right? And that's super critical. We may also have an unfinished or some sort of a finished edge, and so our edge of our fabric we're going to remember is called a salvage edge. If it's an unfinished edge, we're probably going to try and get rid of it. If we're given a piece of fabric that is woven, We need to know which fibers are primary fibers or warp fibers. So we'll be looking for tracers or some sort of piece of information to show us primary fibers. In a prepreg, we'll put it on the plastic, but in a woven fabric, we have to have some sort of a ribbon, a non-strength indicator ribbon in there to show us the direction of the warp fibers, right? Different types of ways of putting those woven fabrics together, and so they give you the, our most common that we see in commercial world, plain fabrics, plain weave. We'll have a crow's foot weave and a harness weave, and so you need to know the makeup of those different types of fiber designs. Within the woven fabric, I shouldn't say that because it doesn't have to be. If we want to gain the advantage of one fiber alongside of yet another fiber, we can create a hybrid type composite build, and so two different types of hybrid designs, and so you should know how those are put together and the terminology that goes with those. So that's a ton of information about fiber technology and the fiber makeup, and so again, fiber being the primary thing that's going to give us strength, right? Alongside in support of our fiber, we're going to be using a matrix, right? Or a glue or an adhesive or an epoxy or whatever you want to call it. And so a couple of different types of glues and then, or matrices, and different ways that they change from liquid state to solid state. Two principal designs. And so two different ways of building. Wet layup, where we mix chemicals and the chemicals react, creating the heat that molecularly bond it and change it from liquid state to solid state. And then we have the prepreg format, where the epoxy has already been applied to the fabric, but we have to apply the heat in order to get that molecular bond to take place, again, to change from the liquid format into the solid format, right? Different materials that we can use for matrix, so single part matrix, which would be like a polyester resin, a two-part, like an epoxy, more typical, and so different ways of building that hardening material, matrix, and different ways that they go together, okay? So the other big thing that we got to keep in mind is this whole idea of how we gain strength in a material. And so for our finished product, we're going to be talking about, well, let me grab some, there, where's my, just had him here, where's my, oh well, okay, so we're just going to grab this. So we got red, hopefully these are good. So, product formation is going to be made up of two parts, right? We know 60% fiber and 40% epoxy, right? And so that is generally a global, it's going to be pretty close to that for most products, right? And so that's the one we want to keep in mind. But what we want to know is manufacturer ratio, right? Manufacturer ratio. And so that's going to be a certain amount of A, how much we don't know, depends, and a certain amount of B, right? And so what we're looking for is we're looking for this A and B. And so when we look at our ratios and being able to calculate it, we need the manufacturer's ratio. And then we're going to find the weight of one component, right? One of those two components. So if we're looking for A, we're going to use the formula WT, the total weight of the finished mix, both A and B, which normally is given, and then the ratio of A over A plus B. So we can use that, or if we're looking for B, we can use the same formula, except we're going to put B over A plus B, right? But always remember that if they tell you the product weight, well, to find the total weight, which is what we need to do of epoxy, we're going to use the weight of the product, and we're going to multiply that by 0.4 because there it is there. The product is 40% epoxy, so that 40% epoxy represents the total weight of the epoxy in the mix, and we need to know that in order to find the parts based on the manufacturer's ratio. So those are going to be our key formulas that we're going to use. And again, if you had to find B here, you could also go WT minus WA, and that would give you WB, right? And so those are going to be key factors in being able to punch through the information. And so what they're going to do is they're going to give you some documents, and from those documents, you're going to have to pull specific information. It's sitting in the way here. And so what you need to do is, I think there's 2 or 3 different epoxies they're going to give you. You need to make sure that the information that you're pulling is correct for the epoxy that they're asking for. They'll say, you know, using 934A, and the product weighs, you know, so much, how much A, right? And so you got to go and find out what is the actual manufacturer's mix ratio for 934A, and then apply it to the math to find the answer, right? And if they ask other specific pieces of information, look for literally the word for word question that they're asking for in that appropriate document, right? So spend the time, make sure that you're using the right information. Yeah. Epoxy or matrices come in different states, right? We can be in plastic sheet, it can be in foaming, it can be in liquid format, it can be in a prepreg. And so different ways of putting things together. And so the prepreg, the main value, the main reason why within aviation we use prepreg is it comes down to one thing, and that one thing is the fact that the manufacturers have the manufacturer's ratio perfect, but they've also integrated that epoxy into the fabric at the exact perfect ratio so that we are pulling the absolute maximum performance out of that fiber for the application. And again, we don't want any more weight, epoxy or fiber than we need. We want that perfect ratio, and if we get the perfect ratio, everything will work at its absolute highest strength level. Any other change from that perfect mix, we get weakening, either from too much epoxy and it being brittle, or not enough fiber, too much epoxy or too much fiber, you don't get the proper strength because it's not supported properly, right? So that's the value of prepreg. And so the prepregs come with plastic on both sides, and we're going to peel one side off, place it over our mold, work it in with a squeegee, make sure there's no bubbles, and that we get perfect contact, peel the top layer off, and then continue that process to build up our product. And then we're going to put the covering layers on it, vacuum bag it, and most important with prepregs is we're going to add heat during the curing process. Okay? And we'll talk more about that, I think, as we go along. We want to understand that, again, most of the mixing of epoxies is going to be done by weight. Always do it according to manufacturers. If we're doing wet layup, we've got the shelf life, which is a drop-dead date for the product in its base format. We've got pot life or working life. As soon as A and B get integrated, we're up against the clock. We've got to get it wetted out, the material wetted out, vacuum bagged and sealed off and ready for curing within that pot life. We don't want to have anything in the buildup that would cause a weakening. So we're going to make sure that if we're doing any sanding and repairing, we're using stuff like reagent solvents to make sure we get perfect contact on clean surfaces, and that we get everything done before we start to see that change in material when we're talking the epoxy. If as soon as we start to see any sort of a viscosity change, it's time to stop and mix up some new stuff so that we can have full integration of the matrix into the fabric. We may heat the material or heat the product up after cure to bring it to full strength faster if we need it to be strong for the next process and whatever the build may be. And so that's important. Understand the 2 different ways of building a composite product. It can be strength through layers, so laminate construction, or rigidity through box design, or sandwich construction. Each has its advantages depending on what it is you're doing with it. And so principal strength comes through laminating, through multi-layers to gain strength, but we can also have a relatively strong product that has great rigidity through a core and layered surface top and bottom, right? Creating that box section which gives us the rigidity and strength. So our core materials in a sandwich construction can be honeycomb, and there's lots of different types of honeycombs, and each one kind of has its own use and advantage, so it's a good thing to know. Synthetics like foams and that, which are more formable and then coverable in a laminate, or not a laminate, but a sandwich design. And then wood is something that could be used not within the aviation field, but is a core material that's used in other industries. We've got our base equipment. Again, a good pair of scissors is probably the most valuable tool you have in a composite shop. And then we're going to get into the actual process and understand the additional layers that we will place on our product after we have, built it up. So we need to have a separation layer on the bottom so that our composite thing doesn't glue itself to the form. We need to have some top layers after we've built the stack up, right? And so those top layers include a possible layer of peel ply. If we want a rough surface when we're finished, we place it on with no additional epoxy. It gets basically glued into our product, and then we rip it off once it's solid, right? Gives us a textured surface for further application of epoxy or paint. There's also, that's a possible layer. Very likely we're going to be using a perforated ply layer. It acts as a release because it's a gloss coat, but it's got the holes in it which allow excess epoxy to come out, and so perforated ply controls the rate of bleed coming off of the stack up once under pressure. It's got to have somewhere for that excess epoxy to go, so we're going to have our breather bleeder, and so it does two things. It sucks up the excess, but it also is going to be connected somehow to our vacuum bases, so we make sure that we've got even vacuum over the whole surface, right? Potentially a cull plate over top of all of that, depending on if you're doing a repair and you want even pressure over a very flat surface, usually using repairs with a protective layer of plastic underneath the cull plate to give us a nice finished surface, and everything's sealed down with sealing tape and bagging film, right? It will be vacuumed, either using a pneumatic source of vacuum or an electric vacuum pump. Could be put inside an autoclave, which provides both heat and vacuum, and most importantly, a pressure, increase in pressure, right? If we can get more pressure between those layers and get a tighter finished product, we're going to get a stronger finished product, right? And so that's the main value of having the autoclave. We're going to put things together, composite parts, so we're going to have fasteners that both integrate themselves into or on top of components, and so we'll have inserts, all kinds of different ones, both male and female, and so they can be installed into like a honeycomb structure using a filler like microballoons and epoxy to fill the material and adhere the composite insert to the main pieces of skin. Fillers can be used for repairs, both inside of a composite like a sandwich construction material, or maybe even as a surface filler if the top damage is very small. And so there's different types of materials to which we use in fillers. The last couple of things are related to some of the weaknesses of a composite structure, and the two primaries being lightning strike dissipation. And so if we have an airframe and we need to have some sort of lightning strike ability to pass that electricity through the airframe, we're going to use either some sort of metallicized fabric as part of the buildup, or we're going to use something like a spray coat of material that will allow that conduction of the electrical power through the structure. And so if we do a repair, we're going to have to make sure that when we do the repair, we're providing that electrical path across the repair area. So if it's a metal fiber, we've got to make sure that it's in contact with the other metal fiber, and then somehow after the fact we'd have to go and do some sort of a conductivity test, verifying that the repair material is in contact with the base metallic material, and so you'd use something like an ohm meter. And then the other thing we have to be careful of course, is chemicals. Not so much for the fiber, but the matrix. And so we want to be careful with the use of nasty chemicals around our exposed composite material with the potential of softening if they come in contact, right? So something we have to keep an eye on. I think that's it. So the primary thing you want to cover is you want to know your fibers, you want to know your matrix, you want to know how the two of them come together to create the strong finished product, and those are the keys if you look at that sort of stuff related to how and the advantages of building in the composite design. So hopefully that's a pretty quick overview, but I hope that'll give you some basis for being able to do better on the exam. So there's some great reading to be done in the FAA manual. That's a great resource. A quick review over the PowerPoints, and you should be in good shape for writing T6. Good luck.